Alright, 3.2 Exponential Decay. We're going to be connecting to negative exponents. To do that, we need to understand what a negative exponent is. Negative exponent means you flip the base and raise the power to a positive value. So again, a negative exponent is not really a negative, but it's a rule. It's a rule that says, really in tiny words, flip the base. Well, we don't look at it as a negative here in the exponent, but we use it as a rule. Once we apply the rule to the base and flip the base to be 1 over a, we can now make that exponent positive. So, a to the negative n is equal to 1 over a to the positive n, and that means the numerator gets the n and the denominator gets the n. That means that 1 to the power of n is going to equal 1. A to the power of n is still a to the power of n. The reason why the numerator stays 1 is, think about it, 1 times any possible number that's up here. 1 to the power of 100 means 1 times 1 times 1 times 1, where there's 100 ones. Anytime you know that is when you have 1 multiplied by 1, the answer is 1. It doesn't matter how many ones we have, the answer will always be 1. Now another concept is a to the power 0. What is that? Anything to the power 0, obviously with the exception of a being 0, because in the first question, if a was a 0, the denominator would be 0 and the answer would be undefined. And the second example, 0 to the power 0, has multiple different answers, and you have to use calculus to solve why. I don't recommend it, so let's move forwards. A to the power 0 is equal to 1. The reason why is, think about it. If I have a number, a power, divided by itself, that is equal to 1 when you cancel. Also, a power divided by itself is also equal to the base to the power of 0. So that means that these two folks are actually equal. Example number 1. Evaluate each of the following. 3 to the negative 2, 6 to the negative 2 times 6 to the 3, 4 to the negative 2 to the power negative 3, divided by 4 to the power 8. So, first one. 3 to the negative 2 is equal to 1 over 3 to the power of positive 2. 1 squared is 1. 3 squared is 9. The answer is 1/9. Let's go to the next one. 6 to the negative 2 times 6 to the 3. You add the exponents. You get 6 to the power 1. Anything to the power 1 is just that number. The last one. Well, we need to simplify this. This we have to multiply to get 4 to the power 6, divided by 4 to the power of 8. What do we do next? Is we take the base of 4 and subtract the exponents. We have that as our answer. What do we do now? Take the negative, flip, and change it so that let's say the question asks us to make it a positive exponent. You take the negative exponent, flip the base, you get 1 over 4 to the power of 2. Why is it 1 over 4 to the power of 2? Let's look at this example here. 4 to the 6 divided by 4 to the 8 looks like this. What are we going to have? We have 6 4s up here, 8 4s down here. Where are we going to have more 4s? The answer is at the bottom. So this is equivalent to 1 over 4 squared. Knowing the negative exponent, we know that that is equal to 1 over 4 to the power of 2, which equals 1 over 16. Guess what? These values are the same, although we took two different approaches. All right, example number 2. Simplify using positive exponents only. So here's an example where you may not start off positive, but you must have a final answer with positive exponents. So you must have positive exponents as the final answer. Here are two examples. And the third one, what do we do now? Well, looking at here, we have 3 powers multiplied with the same base. What are we going to do with the exponents? Well, hopefully, you're thinking of adding them. Turns out that the answer is x to the negative 1. Question wants positive. So how do I make this a positive? Remember that a negative exponent means flip the base. So I flip it, and it comes to the power of positive 1. 1 over x to the power of positive 1 is just, sorry folks, is just 1 over x. Let's go on to part B. How do I simplify this? Well, take the m's and simplify the m's. That gives us 3, because 2 minus negative 1 is positive 3. Take the second one. Negative 3 minus 2 is going to give us negative 5. We don't want a negative exponent. We want everything positive. So it'll be m over 3, m to the power of 3 times 1 over n to the power of 5. Well, that's equal to m over 3 times n to the power of 5. And folks, you could easily have gone from this step over here down to this step in the end without showing this middle step. All right, next one. 3 to the negative 3. Why does the 3 get to negative 3? Because this negative 3 applies to everything inside that is a product. If it is a sum, you cannot do this. This only can be done because all inside here are individual products. That means there's multiplication between everything. Negative 3 can go to each piece, so that you have 3 to the negative 3, u to the negative 9, because you're multiplying, and v to the positive 6. What do we do now? Well, only the negatives have to move, so that we have v to the 6 on top, 3 to the negative 3 goes to the bottom, which gives us 27, and u to the negative 9 moves to the bottom to give us u9. And that is the final answer to part C. Example number 3. Evaluate the following. To do this, we need to understand the exponent rules. Exponent rules says that each of these can get the negative 2. The reason why is because the negative 2, can be applied to only products that are raised to that power. This is a product, so each one of these can be multiplied to the exponent on the outside. You get, some people decided they wanted to do the inside. So let's try the inside then. 1 over 4 all squared is 1 over 16. 2 times 2 over 5. What is 1 over 16 times 2 over 5? Well, that's equal to 1 over 40. The reason why it's equal to 1 over 40 is because this is the top will be multiplied to give you 2. The bottom will give you 80, and you can reduce it. This is the way I was taught. Without a calculator, I know that 2 and 16 can reduce each other to give you 1 and 8. Knowing that, I have a numerator of 1 times 1 and a denominator of 8 times 5. So it's 1 over 40 to the power of negative 2. I then take the negative on that exponent, right there, that negative that was there, and we will flip the base to give me 40 to the power of 2. 40 to the power of 2 is equal to 1600. All right, next example. Exponential decay functions, such as the following, mean as x increases, so as x approaches infinity, the y values will decrease. The y values will approach operate in a negative value, so they decrease. The y values are going in a downwards direction. Or, in this case, there's another example where you have, as x values are increasing, the y values are decreasing. So the y values are going down. The graph decreases at a decreasing rate. They have repeating exponential pattern of finite differences that the ratio of successive finite differences is constant. If you have a product, for example, if you're doing delta y, delta x, delta y, delta y, and you notice that all the values have a product of 1/2 or 1/3 or a quarter, it means the number, not the sign, don't worry about the sign, but the number itself indicates that there must be a decrease. All right, let's stop here and go on to the next video. See you in the next video.